So let us now move on to question 60. So this is where things start to get a little bit more difficult now. So I recommend pausing this video and having a crack yourself. So one of the methods for estimating the temperature at the center of the sun is based on the ideal gas law. Okay, so that's kind. They're giving us the equation to use already. So if the center is assumed to be a mixture of gases whose average molar mass is 2 grams per mole. Okay, so this is interesting. We're given a molar mass. And if the density and pressure are 1.4 grams per centimeter cubed and 1.3 to the 9 atmospheres respectively, calculate the temperature. Okay, now this is where things are going to be a little bit interesting. So, what we can do is, don't be confused about centimeters cubed. They just do that to try and get a little bit of panic out of you. Centimeters cubed is the exact same as 1 milliliter. So it's grams per mil. So you're familiar with those units, that's okay. So the first thing I'm going to do is, again, I'm looking at our density here. I don't like the fact that it's in mils, because when we're dealing with gases, similar when we were looking at stoichiometry and properties of liquids, is where you want to use liters. So I'm going to first convert this to liters. So 1.4 grams per mil is the exact same as saying 1400 grams per liter. Now, we now have a mass of our gas in grams per liter. And that's good because remember, our ideal gas law, which was given to us here, is PV nRT, and our volume has to be in liters. So what we've done here is not only do we have our volume now, so we'll do a little checklist. So temperature, we don't know. That's what we want. R is our constant. Moles, we don't know. Volume, we do know because we've just figured it out. We've just converted it so that it's 1 liter. And our pressure, we have as 1.3 times 10 to the 9 atmospheres. So this is where we sit here and go, well, okay, we've got 2 unknowns. What can we do here? So it's like, well, how can I calculate moles? So this is when I sit here and go, okay, well, what is moles again? So I go, moles is equal to mass over molar mass. So instead of looking for moles, I now go, okay, do I have a mass or a molar mass? And this is when I go, oh, hang on, yes, I do have a mass. We have 1400 grams. And it's like, do I have a molar mass? Yes, I do. That was given to us in the question. So I know that's 2 grams per mole. So that means our moles is 1400 divided by 2, which is 700 moles. So that's a huge number. You know, that is a massive number of moles. But in saying that too, this is where we look at our answer and go, does it make sense? Does it fit the question? So if you had a question that said you were in the lab and you had to make up this concentration and you got 700 moles, probably not, okay? That's probably not correct. But here we're dealing with temperatures and gases in the center of the sun. That is both boiling hot and massive. So 700 moles is probably not that much out of the question. So that's what I mean by relate your answer to the question, see if it makes sense. So now that we have our moles, which is 700 moles, we can now use our ideal gas law. So again, we want to calculate the temperature. So I'm going to move our moles and constant over. So now we plug and chug. We go 1.3 times 10 to the 9 atmospheres multiplied by 1 liter divided by the moles, which is 700 mole, multiplied by the constant, which is 0.0821. So now we just pump that into the calculator, and that will give us a total temperature of 2.3 times 10 to the 7 Kelvin. Because remembering, our temperature is always in Kelvin. And that is our total temperature, or estimated temperature of the sun. Okay, so looking now at question 63, page 246. So given a sample of gas at 27 degrees, so I'm going to underline that, and already that's catching my attention because this is Celsius. At what temperature would the volume of the gas sample be doubled with the pressure remaining constant? Okay, so this is interesting. So what temperature would the volume of the gas be doubled? So this is where I'm going to go, okay, ideal gas law, so PV, nRT. So which variables are we talking about here? So sample of gas at 27 degrees Celsius. So we've got temperature. That's awesome. At what temperature? Yes, that's fine. Would the volume, so we've got volume, pressure remaining constant. So we don't want pressure. We don't need moles, and we don't need our constant. So I'm just going to erase those. So we have V and T. So I'm going to move everything to the left, which means that we're going to have V1 over T1 is equal to V2 over T2. So this is the equation that we're going to be using. Now, the first thing I'm going to do is I'm going to start to associate our sort of unknowns here with some of our information. So given a sample of gas at 27 degrees Celsius, so that's going to be our T1. At what temperature? So that's going to be at T2. Would the volume of the gas be doubled? Okay, so this is interesting because we're not given any volumes. However, we are told that the volume of the gas is doubled. So how I'm going to represent that is instead of putting V2, because we don't know a V2, I'm going to put 2V1 because it's saying that the volume of the gas is doubled. So if I have V1 and I put 2V1, this is saying that the gas over here is double V1. It's 2 times V1. So now I'm going to try and rearrange this formula so that we can get T2 by itself, because that's what we're after. That's what we want to calculate. So I'm going to see that this is a divide. So I'm going to move the T over here. So we're going to have T2 times V1 over T1 is equal to 2V1. So this here is a divide. So I'm going to move this over here. And this is the relationship between V1 and T2 is a multiply. So that's going to turn into a divide. So that means that we're going to have T2 is equal to 2V1 times T1 divided by V1. So what I do here is I'm looking here at our equation, and we've got 2V1 times T1 over V1. Now, we've got V1 on the top, and we've got V1 on the bottom. So these cancel out, which means that we have T2 is equal to 2T1. So our T1 is 27 degrees Celsius, but we need to convert that to Kelvin. So 27 plus 273 degrees Kelvin will equal to 300 degrees Kelvin. So that means that T2 is equal to 2 times 300 degrees Kelvin, which means that the final temperature is equal to 600 degrees Kelvin. Now, we check our question. So at what temperature would the volume of the gas sample be doubled? So it doesn't tell us which unit that we need to put our temperature in. So 600 degrees Kelvin is fine. However, if it did ask for Celsius, we can just subtract 273, and that will give us 327 degrees Celsius. Okay, now this one was a little bit of a tricky question because it straight up involved algebra. It involves a lot of rearrangement and simplification, and this can confuse a lot of people. So just remember, if you have the same item on the top as you do on the bottom, they can cancel. And that allowed us to solve this question. Okay, team, so let's now look at question 73. So at STP, so again, straight away, put a big square around that one. 560 mil of a gas, it has a mass of 1.08 grams. What is the molar mass of the gas? Rhyming accidentally. So again, we've got one of those questions that's trying to put you out of your comfort zone. It's trying to give you units that you wouldn't typically see with gases or that you wouldn't instantly recognize. So the first thing we're going to do is, again, I'm going to see STP, so I'm going to write PV equals nRT. Now, I'm going to write our different units, so pressure, volume, moles, constant, temperature. So the question is asking, what is the molar mass? So already I'm sort of sitting here going, okay, if it's asking for the molar mass, and I know that the ideal gas law has moles, it means I'm going to have to use, so that's where I write this formula down. So that tells me that this one is going to be our unknown. Our pressure is 1 atmosphere. Our volume is 0.56 liters. Constant 0.0821. And our temperature is 273 degrees Kelvin. So what we do is we plug and chug, but we need to get moles by itself. So I'm going to move this R and T over here. So we're going to have PV over RT is equal to moles. So moles is going to equal to, so we pop that into the calculator, and we are going to get 0.025 moles. So now that we have our moles, we have a mass, it's time to calculate our molar mass. So we can go moles, which is 0.025, is equal to 1.08 grams divided by our molar mass. So we rearrange this, so it's going to turn into molar mass is equal to 1.08 grams divided by 0.025 moles, which will give us a molar mass of 43.2 grams per mole. So again, when a question throws some units that you may not be familiar or comfortable with, just have a look and see how do they link together. So straight away when I saw mass and it asked for molar mass, straight away I thought moles. So this is why, especially in the stoichiometry and the properties of liquid sections, I emphasized so hard for having a good knowledge of those formulas, because you will use them in a wide variety of different modules. Okay, our lucky last one, and this one I included for you guys just because of your mid-semester exams, because I know how much we love percent composition. Oh dear. So, a gas has a percent composition by mass of 85.7% carbon, 14.3% hydrogen. At STP, so again, big square around that one, the density of this gas is 2.5 grams per liter. So that's interesting. They've already put it in grams per litre for us, not grams per mil like they usually do. What is the molecular formula for this gas? Okay, are we ready for it? Let's go. So the first thing I'm going to do is, because we're given our percentages, I'm going to assume 100 grams so that it's easier for us to convert those percentages to mass. So we had 85.7% carbon. So that means carbon is going to equal 85.7 grams. Hydrogen is 14.3 grams because it's 14.3%. So now we're going to convert these into moles. So we're going to go mass, which is here, divided by the molar mass. So the molar mass for carbon is 12.01 grams per mole. And the molar mass for hydrogen is 1 gram per mole. So if we have 85.7 divided by 12.01, we're going to get 7.14 moles. And hydrogen, we get 14.3 divided by 1, which means we're going to get 14.3 mole. So what we do now is we divide each of these by the lowest molar concentration. So 7.14, 14.3, it's clearly our carbon. So 7.14 divided by 7.14 is equal to 1. And 14.3 divided by 7.14 is going to equal 2. So just round it to the nearest whole number. And what this step does is it gives us a ratio of carbons to hydrogens. So it means for every 1 carbon, we're going to have 2 hydrogens. So this is going to give us an empirical formula of CH2. Now, the question clearly states a molecular formula. So what we need to do now is we need to try and find out the molecular formula. Now, at STP, now it's important to note that at STP, 1 mole is equal to 22.4 litres. Now, this is where we should start to build a bit of a link by going, okay, we know that at STP, 1 mole is 22.4 litres. We have over here that 2.5 grams, that the density of this gas is 2.5 grams per 1 litre. So we can sort of use both of these to convert our units. So if we know that 1 mole is equal to 22.4 litres, so we can go 22.4 litres over 1 mole. So again, this is how we write our conversion factors. And what we can also do is we can multiply this by our density, because we know that 2.5 grams is in 1 litre. So we can see here that our litres cancel. So we have 22.4 multiplied by 2.5 grams. And we have 1 mole at the bottom. So 1 mole, so we divide it by 1. So that gets rid of, so anything divided by 1 is itself. So this gives us 22.4 times 2.5 is 56. So our only units left on the top is grams. And the only unit that we have on the bottom is mole. So grams per mole is our molar mass. Now, this is the molar mass of our actual gas up here. And we look at the molar mass of our empirical formula over here. So carbon is 12 and hydrogen is 1. So this molar mass is equal to 14. So essentially, we just keep multiplying this until we hit 56 grams per mole. So 14, so times 2, 28. So then we multiply it by 3. So that's 42. We'll add another one, and there's our 56. So that means that the molecular formula is 4 times this, which means it is equal to C4H8. Okay guys, so that wraps up Module 10 Video 2. Thank you all very much for joining me today. I hope you enjoyed my working out of these questions. If you do have any questions, queries, or suggestions, or ideas, please feel free to hit me up at b.grant@griffith.edu.au. If you could all please complete this survey down below, really helps me out a lot. So my name is Brock Grant. Thank you all very much for joining me today, and I'll see you all next time.